Hello everyone, we'll study energy conservation in this video. So we have learned what is kinetic energy and what is a work done by a force. So it's work equals force times displacement times cosine the angle between force and displacement. Now we need to distinguish forces based on how they do work. So we define conservative force first. Conservative force. Now, if the work done by a force depends on only the endpoint of the path, then we call it conservative force. To be more specific, so if you start from this location and you end up with another location, it doesn't matter which path you took. You can go up the mountain, get to the end point. Or you can go this way, or you can go straight. So work done by gravity along these three paths and all other paths that connecting those two positions are the same. The work done by gravity, and we can prove that the work done gravity doesn't depend on this path. So we call gravity is a conservative force. Now the definition is that the work done by the force between 2 points is always the same, independent of which path the object took. And in physics 1, we learn gravity, which is a conservative force. We learn spring force, which is also a conservative force. And if we move on to physics 2, we have electromagnetic force are also conservative forces. And conservative force is special because it allows us to transfer kinetic energy and potential energy. And as I mentioned in physics 1, gravity and the spring force are two conservative forces that we studied. Now, if a force is a conservative force, there are four equivalent definitions. First, it can be expressed as a potential energy as a function of the position and is reversible, is independent of the path between 2 points, 0 if the starting point and end point are the same. Those four definitions are all equivalent mathematically. And of course, for us, we took this definition and then we want to study how it's related to potential energy. Now, on the other hand, if a force is not conservative, which means it doesn't satisfy those conditions, then it's not a conservative force. We call it non-conservative force, like normal force, friction, tension. So all the other forces we learned in this semester, except the gravity and the spring force, they are non-conservative forces. And why we study conservative force is because if you have a conservative force, then you can define a potential energy. And the potential energy was defined as your change of potential energy equals to negative of the work done by your conservative force. Let's call it conservative force. There is final potential energy subtract initial potential energy. So using this definition, you can find out for gravity, you can have the change of gravitational potential energy equals to negative of work done by gravitational force, and it only depends on the height of the object and is u2 subtract u1, and you will find out the work done by gravity if an object move from y1 to y2, the work done by gravity is actually mgy2 subtract mgy1. So we can call this term u2, this term u1. Now we arrive at the definition of gravitational potential energy, just mgy. Y is the height of the object, give us the gravitational potential energy of the object. And the change of gravitational potential energy, of course, is related to the work done by gravity. So in this case, this is the initial position. The object moves to a lower position. Displacement is going down. The gravity is doing positive work in this case. Gravity is doing positive work, right? And then we know change of potential is negative of work done by gravity. And your work is positive, so in this case, when object goes down, displacement is pointing down, the potential energy decreases. Now, on the other hand, if the object going up, the displacement pointing up, gravity doing negative work. Gravity doing negative work. Now, if your work done by gravity is negative, remember, negative of the work done by gravity gives you a change of potential energy. So change of potential energy is positive in this case, which makes sense, right? So when an object goes up, its gravitational potential energy increases. Let's recall work energy theorem. The work done by all the forces on an object equals to the change of kinetic energy. And based on that, we can derive what is conservation of mechanical energy. Now first, the mechanical energy is defined as the sum of kinetic energy and the potential energy. Now there is a condition: if the only force that do work on the system is only conservative force do work, then mechanical energy is conserved. We can prove this. The only force do work are only forces do work are conservative forces. Only conservative forces do work on a system. So the work done are all conservative forces equals to, but the total work equals to the change of kinetic energy from the work energy theorem we just reviewed in the last lecture, right? And I also know work done by conservative force equals negative of change of potential energy. Now, negative change of potential energy would be negative final potential energy subtract the initial potential energy. Now, it also equals to K2 subtract K1. So this is negative U2 plus U1 equals K2 minus U1. And if you rearrange that, you put the K1 on left-hand side, all the ones on the left-hand side, all the twos on the right-hand side, we arrive at this equation. And I do know mechanical energy. Mechanical energy is K plus U. You can see the final mechanical energy equals the initial mechanical energy at all times. If only the conservative forces do work on a system, so the mechanical energy always equals to the initial mechanical energy and is always a constant, so we call mechanical energy conserved. So now let's try to remember the only force do work is conservative force, then mechanical energy conserved. If only conservative force do work on the system, the mechanical energy conserved. And now, of course, if only gravity is doing work on the system, then K plus gravitational potential energy is a constant, is conserved. So let's do 2 examples on this. So this is a problem we studied before, right? We use projectile motion to study this problem. Let's say you eject something with initial horizontal velocity 16.5 meters per second. It flies in the air, projectile motion. It drops 22 meters. We want to find out what's the speed of the ball before it strikes the ground. So we need to think whether mechanical energy is conserved in this process, right? What are the forces acting on the ball? I can only see gravity. So there's when the ball is flying in the air. Now, of course, we need to ignore air resistance. If we ignore air resistance, when the ball is flying in the air, the only force acting on the ball is gravity. So, of course, only gravity is doing work. Now, remember, it's not about how many forces acting on the system. You can have non-conservative force acting on the system. But as long as non-conservative force doesn't do work, mechanical energy will be conserved. So in this case, while we don't have non-conservative force, only gravity acting on the ball, only gravity doing work. So of course, only gravity do work, which give us mechanical energy. Conserved. So we can build the mechanical energy conservation equation now, which is K1 plus U1 equals K2 plus U2. Okay. So K1, 1/2 mv1 squared. K2, 1/2 mv2 squared. U1 mgh1, U2 mgh2. And I do know h1 is 22 meters taller than h2. I can just choose my h2 to be 0. So my h1 is 22 meters. Okay. And I do see m on each of the terms. So actually I can divide m on each of the term and I choose h2 to be 0. So I can arrive at this equation. Now I do know what is V1, I do know what is H1, so I can solve for my V2. In symbol, it should be V1 squared plus 2GH1. Plugging all the numbers, I find my V2 is 26.5 meters per second, which is consistent with what we get before, right? Okay, next example. Tom skates down from quarter circle frictionless ramp. The radius of the ramp is 3 meters. The mass is 25. Tom and his skateboard. Find the speed of Tom at the bottom. Now to solve this question, when Tom is skating down, what are the forces? What are the forces acting on Tom? So we have normal force, right? And gravity. Apparently, gravity is doing work because the height drops. Does normal force do work on Tom when he skates down this semicircle? So let's say This is normal force, and then this is the velocity. Velocity will be always perpendicular to normal force in this case. So which also means the displacement at this instance is perpendicular to normal force. We find out that normal force always perpendicular to displacement, always. And we recall that the work is force times displacement times angle between force and displacement. And the angle between normal force and displacement is always 90 degrees, so cosine 90 degree gives us 0. Normal force doesn't do work. We do have normal force acting on top, but normal force doesn't do work. So the only force doing work is gravity. The only force doing work is gravity. So we have mechanical energy conservation. So we can write down the conservation equation: 1/2 m v1 squared plus mgh1 equals 1/2 m v2 squared plus mgh2. Now it's a quarter circle, so if you draw it, we can find out the distance, the height between h1 and h2 is just the radius r equals 3 meters. Right? But before I can choose h2 to be 0, then h1 is 3 meters. And scale down from rest, so initial kinetic energy is 0 because your v1 is 0. From rest, v1 is 0. And h2 is 0. So I can solve for my v2 now. Solve my v2. If you solve it in equation is 2gr. The plugging all the numbers is 7.74 meter per second squared. So let's rephrase. What is mechanical energy conservation. What's the condition? The condition is that only conservative forces doing work on the system. Then the mechanical energy of the system is conserved, which means kinetic energy plus potential energy is a constant. So you can build a conservation equation, which is one equation for you to solve the program. So we'll move on to momentum in next lecture video. Thank you for watching.